This is a problem on tension member, and you have been asked to determine the design tensile strength of the tension member. What is given here is a angle section 100 by 100 by 10, which has kind of been connected with a gusset plate of 10 mm thickness using 6 mm fillet welds, and the grade of steel is Fe410. So this weld, what is being provided, has been shown in this figure over here. So we'll go ahead with calculating the design tensile strength in three different criteria, that is yielding, rupture and block shear. So when it is a question of yielding, it is given by TDG, which is Ag into Fi upon gamma m naught, clause 6.2 of IS 800, page 32. So the gross area here, it will be the area of this connected leg plus the area of the unconnected leg or the outstanding leg. So if we calculate that, or even this can be taken from the steel table, so it comes around 1900 mm square over here. So this gross area into 250 divided by 1.1 factor of safety based on the yielding criteria. So it is 1.1. Table 5 will give you that. So from this TDG, what you get is 430 on 0.8 kilonewtons. This is the strength governed by yielding of the gross cross section. This gross area you can directly refer to the steel tables. You can take it from there, and you can even go for calculating this gross area. That we'll see how we can do that, but that will have a slight difference compared to steel table. A small difference may come over there. So this is one strength what we have calculated. Now the second strength is due to the rupture at the critical section. So in that case, if it is an angle section, it is expressed as TDN, which is equal to 0.9 ANC Fu upon gamma m1 plus beta into Ag naught into Fi upon gamma m naught. So this particular strength, what you find is in clause 6.3 in page 32 and 33 of IS 800. You'll get this particular equation over there. So first is we'll go for calculating what is the net area of the connected leg and gross area of the outstanding leg. So here the net area of the connected leg, what you have is 100 is the length of this leg or width of the leg minus half the thickness. Half thickness will be considered in connected leg and half thickness will be considered in outstanding leg. That's why I have deducted half the thickness over here. So this will be the width into the thickness of the angle section, which is 10 mm. So it comes out as 950 mm square. Similarly, uh, the gross area of the outstanding leg will be 100 minus 10 by 2 into 10. Again, it comes out as 950 mm square. So both of them will remain same in case if it is an equal angle section, because we are not made for any deduction of bolt hole. It is a welded connection, so you will not come across any deduction of bolt hole in this A and C, that is in net area of the connected leg. So 950, 950, if you add them together, it will be nothing but the gross area which we had considered in this TDG. So gross area 950 plus 950, it is 1900 mm square. So this is the gross area of that angle section, how you can calculate. In case if you don't have the steel table, if you are not able to get the steel table, but always prefer to take from the steel table. And if you compare this gross area with steel table, there will be difference what you will find over there. But in this case, what I require here is, while calculating the rupture strength, I need these two, ANC and Ag naught. My purpose is to calculate ANC and Ag naught. So the net area of the connected leg, it is coming 950 mm square. Gross area of the outstanding leg is also 950 mm square. Since it is equal angle section, both are coming same, and also we are not done any deduction for bolt holes in the connected leg. That you should keep in mind when it is a case of welded connection. There is no deduction to be considered over here. And W will be 100 mm. So this width of the outstanding leg 100 mm. BS will also be 100 mm. So in our calculation, in this T beta factor, we'll require these W and BS. BS will be from the edge of the angle section up to the connection. So in this case, it is edge from edge up to this weld line. So it will come out to be 100 mm over here. And W, width of that connected leg. So this we have seen in this IS 800 part. BS will be equal to W in this case, in case of welded sections. So BS and W will remain same over here. So that's why it has been taken here both as 100. So next is we require length of connection. So in this case, two weld sizes are there. So this will be in bolted connection from the first bolt up to the last bolt will be your length of connection. Here what you need to do is you take the average of these two lengths of the weld. So length of the weld 140 mm along the loading direction plus 60 mm. So starting point of the weld and this is the end point of the weld. But here in this case both welds are of not the same length. So you take the average of these two, which comes out to be 140 plus 60 by 2, that is 200 by 2. LC will come out to be 100 mm. So BS and LC have been used in this calculation of beta. So beta is the shear lag factor 1.4 minus 0.076 into W by T into Fi by Fu into BS upon LC. So W was 100 mm, T thickness of the angle 10 mm, Fi and Fu 250 and 410, yield and ultimate tensile strength of the material, PS 100 mm as we have seen here, LC which was calculated taking the average of the two weld lengths, it is 100 mm. So PS beta will be 0.93 from this, and you should see that it is not less than 0.7 and it is not more than 1.44. So these limits are there. So our beta values between these two limits. So I can adopt this as my beta while calculating TDN. And when you substitute for all these ANC, AG naught, beta, and the stresses Fu and Fi here, the design tensile strength due to rupture at critical section comes out as 481.23 kilonewtons. This is the second governing strength over here, that is based on rupture at critical section 481.23. The next is the block shear. So in case if it is a block shear, you'll come across shearing plane and the tension plane here. So the gross area and the net area along these two planes have to be calculated. So they have been done over here. Again, we'll find that the bolt holes are not here. So we'll see that the gross area along the shearing plane and the net area along the shearing plane will be the same. So these two are the lines along which shearing will occur. This 140 and this 60. Along these two weld lengths, shearing will be experienced. So total area along these shearing line will be 140 plus 60 into the thickness of the angle. So that will be 2000 mm square gross area, and even the net area along the shearing plane will remain same, 140 plus 60 into 10, that will be 2000 mm square. Now the tension plane will be here perpendicular to the loading. So this will be the tension plane which is 100 mm because this angle section is ISA 100 by 100 by 10. So this width of the angle will be 100. So it will be the net area or the gross area along the tension plane will be 100 into 10, which is 1000 mm square. So using these areas, that is AVG, ATN, one of the block shear strength comes out to be 291.95 kilonewtons. And later if I go for taking the rupture to be taking place along shearing plane and yielding to be taking place along tension plane, from that calculation you'll find that the block shear strength comes out to be 363.59 kilonewton. So compare these two, whichever is least, that will, and comparing these two, whichever is least, that will be considered as strength under block shear. So out of these two, 291.95 is the least one, so that will be considered as TDB, strength in block shear. Now if you want to report the design tensile strength, you need to look for the strength in yielding TDG, rupture TDN, and block shear TDB. Compare all these three and see which one is least. That will be taken as the strength in tension, design strength under tension. So you have the three values. What are there here? Out of the three, the least one is TDB, which is 291.95 kilonewtons. So that has been taken as design strength under tension over here.